In this video, we're talking about some optimization technique for the parameters of deep neural net. So in particular, we will discuss the initializations, the activation, and normalization of the network parameters. So here we go. First, let's talk about some challenge that happen in optimizing neural net. And optimizations in machine learning is the process of finding the parameter theta of a model that significantly reduce the cost of a loss function j, with parameterized by the parameter theta, would typically include the performance measure evaluated on the entire training set, as well as some regularization parameters that we have seen before. So the way we can frame the machine learning problem is that we can frame it at an optimization problem to minimize the expected loss on the training set. And this typically in the optimization framework is called empirical risk minimization. So the formulation for this is the expected loss of the data x and y based on some loss function. F here is the model that we see, and then we compare the output of the model and the label, which is the loss, and this is calculated not simply by just the average error, which is calculated between the predictive value and the label. This is the average, so the weight, the sum. So that's simple enough. But our assumption is instead of optimizing the risk directly, which is very difficult to do because we never be able to collect all the x and y, but we can optimize the empirical risk, which is empirically collected based on our training set. And if we optimize this empirical risk, hopefully we're able to decrease the actual risk as well. Now, optimization for the neural network, unfortunately, that the empirical risk minimization approach is prone to overfitting, especially with model that have high capacity, such as a neural net. We talked about this overfitting on the last lectures because the neural net just simply memorize the whole training set. So with that, in deep learning, we take in a slightly different approach. And our approach is minimize the error by mini-batch stochastic methods. So what does that mean? Minimat means that you take the data batch by batch. So instead of training on the entire data set, you will train it on only a small subset of the data set. And the size of the batch or the mini batch is driven by hardware, by parallelizations, or by available memories. But it's common to select a power of 2 at your batch size. So you can think about it, a power of 2 like 32 to 56, or sometime even 1024. And it is crucial that this mini batch are selected randomly in order to work. That's why this method is stochastic. Now, to compute the gradient of the loss with respect to the parameters, we need these formulations. This is very similar to what you see before, but this is the gradient of the loss with respect to the parameters. And then we can update the parameter in the directions of the gradient as seen in this formulation. And epsilon here is the learning rate. So we've seen this in the training of the neural network before. So I'm going to use G at the gradient from now on to kind of see that's how we can calculate it. But that is how the optimization will work for neural network. Okay. So there is a few annoyance that happen in the optimization of neural network, namely local minima. At the local network is non-convex. This possible to have many local minima, and with local minima, the optimizer kind of gets stuck in a this is the local minima that perform nearly as well as the other, but sometimes you get stuck on this local minima, which is sort of a valley here in this loss function that would never really have a good cost associated to it. So when you end up with here, it's very can pose a serious problem for the algorithm. Now, another problem we have is called plateau. And what happened is this cost functions here become very flat. And what happened when the loss become very flat is there's no gradient for you to compute. So at this time, you can't really change the parameters anymore because it's become, it doesn't make any difference to the loss. Now, local minima and plateaus happen in the training of the neural net, but saddle point is happen even more, and because this is a highly non-convex, highly dimensional convex functions, there's another point with zero gradient. So you consider this function here in 2D here, and this is the vertical is a loss. You can see at this perspective, if you look at the dimension on respective of x1, look like we can find the minimum here, right? This is the smallest point if you go into this direction. However, if you go into the direction of x2, this point now become a maximum. And that's the situation with the saddle points, right? Some point around saddle point have greater cost, while other have lower costs. And this is a very hard situation because the gradient is zero, and you thought that you accomplished with the lowest cost, but actually you can go to other points that have lower costs. So training deep model that able to tackle the complex problem, such as the visual perception task, typically you need to train a very deep network with perhaps even hundreds of layers and thousands of neurons. And training a deep network have without some issue associated with that. First is the training can take extremely slow. And as we will see firsthand, this do take time. Secondly, because we're dealing with thousands, if not millions, parameters, this is very risk to overfitting to the training data. And lastly, this particular neural network is facing the tricky vanishing gradient problem. So what is the vanishing gradient problem? It happens when you passing the error gradient back and forth using backprop from the input, go to hidden layer, go to output, back and forth, and use that gradient to update the model parameters. What happens is when you have a very deep computational graph, repeatedly applying the same operation per each node in the graph again and again, making the gradient smaller and smaller. And if you keep computing that gradient and pass it through the node, at some point the gradient become very small, and so the weight updates no longer work, and the weight become virtually unchanged. And this is the vanishing gradient problem. So numerically, if you think about it, if you keep updating this really deep neural net and say it's 100 layers, and each of the layers you simply just having a 0.5, and if you keep multiply by 0.5, eventually you get to a number that's so small that's really have no significance to your computation. And that's what happened with the vanishing gradient. And you can see the visually on to this vanished point of a in state row, and eventually at that point then nothing changed in the parameter anymore. Now there is another problem associated with the neural net is the exploding gradient problem, and this is just the opposite of the vanishing gradient. So again, if you repeatedly multiply the matrix at any time step in your computational graph, you may run into a risk of this number blow up through many repeated multiplication. So as the gradient go bigger and bigger and pass through the network, some of the layer may get really large weights updates, and the network become very unstable or explode, right? So for example, if I have some numbers quite small, like 1.5, right? So you update it. But if you keep multiplying this like 100 times, now you get a number so huge, it has 17 zero after it, and which point the network will be diverged or explodes here in this case. So you don't want your network to be, the gradient to be vanished, and you don't want the gradient to explode. And by the way, this vanishing gradient is the reason that deep neural net was abandoned for over 2 decades until its recent renaissance. So optimization of the neural net, there's a few considerations we have to keep in mind. How do you initialize the weights so that they don't saturate? Activation, how do you solve this gradient problem by choosing the appropriate activation functions? Normalization, how do you get the model to learn the optimal scale of the parameters? Optimizers, we talk about gradient descent, but is this good enough? We also have adaptive learning rate, which is some optimizer will use to make the training faster. And finally, we even looking at the second order training method, which is make use of the second derivative. Now, this video, we're going to cover the first 3 parts of this optimization process. So here we go. Number 1, initialization. Now, the initialization is very important with neural net because with the gradient descent and iterative algorithms, which require the user to specify some initial point from which the training begin. And this is very important. Depending on where you initialize your parameter, you might end up with different results, right? So deep learning is strongly affected by the initialization. So we want to initialize the parameter so that the signal won't vanish nor explode and saturate, right? So what we should really look into is the symmetry that the signal pass between different units. If the symmetry is break and you have a very deep network, eventually it will run into problem of vanishing or exploding, right? So to keep the flow symmetrically, Xavier Gerard and Joshua Benjo, with his advisor, argue that we need the variance of the output of each layer to be equal to the variance of the input. And that gave rise to the Xavier initialization for logistic activation function in 2010. So this heuristic strategy of initialization led to current success of deep learning. And they are quite simple. All you have to do is instead of initialize your network, say 0 weight, which you shouldn't do, you initialize to either some random, a uniform distribution with either negative weight or positive weight calculated by this. So this will be different from layer to layer, depending on how many input that layer receive and depend on how many output that layer produce. And that would help initialize the weight for that particular layer, right? So square root of 6 over n input plus n output. And you initialize it this way, what happened is the variance will be equal from the input to the output, which was the point of Xavier initialization. Now you can do the same with the normal distribution here with 0 means and standard deviation using these formulations, right? And so that is Xavier initialization. Now, another researcher, he and his group extend the Xavier initialization applying to multiple activation function. And this is the summary of the initialization depend on whether it's logistic, hyperbolic tangent, or tanh, or the ReLU and its variance. So if you decide to use uniform distribution, you can use this formulation to calculate the weight. And if you use normal distribution, you can use this to calculate the standard deviations to initialize the weight randomly. Well, not randomly, based on some Gaussian normal distribution, of course. Okay, so we mentioned a bit of using Keras. You can implement this initialization in Keras. Simply use this keras.layer.dense and initialize it, kernel initializer with he normal. Next up is activation. Activation quite important. The choice that you pick the activation function will affect the performance of your network. And a poor choice will lead to vanishing, exploding gradient. So in nature, typically roughly sigmoid activation functions for biological neuron, but it turns out that other functions like ReLU can behave much faster and better. So if you look at sigmoid, for example, sigmoid function have really three main parts. The middle part is really a linear function, right? Just grow linearly. And then they have two ends where the signal kind of saturating around 0 here and around 1. So what happened when the signal is saturating here is that doesn't matter if this signal changing to be larger, smaller, the output will be just around 0, right? Or here in this case, if the number grow, that's just saturating around 1. And when you have sort of constant in activation, there's no any gradient for you to propagate, so which is a problem. So with ReLU, it's a little bit better. If you remember, ReLU here having two parts. This part right here grow with the input, so input increase and output will increase linearly. And they have the other part of ReLU where if you have negative input, then the output just simply 0, right? So ReLU may be great, but it's give also a problem of dead neuron. Meaning that the output always 0 when then nothing really useful come out with output 0. So to solve this, you can use a variant of ReLU called leaky ReLU. So instead of outputting 0, leaky ReLU would outputting some small negative numbers for negative input, so that you have at least some signal to propagate your gradient. So it's slightly improvement over ReLU. Now, can we do better? And the answer is yes. We can improve using a what called exponential linear unit, or ELU. And ELU proposed by Clevert in 2015 that proved faster convergence and higher accuracy than ReLU. And the way it's worked is pretty simple. It's keep the same way when you have a input that greater than 0, just like ReLU, but when the input is less than 0, then it do some exponential functions here, scale by alpha, and this is some shifting here. I should better show you on the graph and comparison with leaky ReLU. So ELU kind of leaky ReLU as well, except that this would be a smooth exponential curve that you can manipulate. Right, so you have -1 here, I guess, because it's here, and you can manipulate how well you want it to behave. Now you can use that directly using in-Keras with activation equal CELU. So CELU here is the scale version of ELU to specify some value of alpha here. But the nice thing about this compared to ReLU is it give several advantage. Number one is that the signal now is smooth, so that you can have a derivative any point in the function compared to this one where you couldn't differentiate when the signal is 0 at that point because it's not a smooth function. The other one is you avoid from dying neuron, right? So no longer output 0 here. It's output something that is more workable, like a negative numbers in this case. And it's have non-negative, non-zero gradient throughout the function, which is really nice. Okay, so the third consideration for optimizing your deep neural net will be the normalization process. And the initialization that we talked about earlier reduce the vanishing exploding gradient at the beginning of training, before you start the training, right? But as the training go on, there's no guarantee that this parameter can go rogue and become vanishing or exploding. So what do you do then? Sergey Ioffe and Christian Strategy in 2015 proposed a technique that keep the gradient and the parameter at bay called batch normalization. And what batch normalization does is add an extra operation before the activation function in the neural net. And that process basically doing zero centering and normalizing the input, and then scaling and shifting the result or the output into some optimal scale. And the really nice thing about this is that the extra process always shift the output of the network back to the optimal scale that learnable during training. So in particular, the batch normalization layer would try to learn 4 parameters per node, and that's scale, offset, mean, and standard deviation. And the formulations are provided down here, but it looks complicated. It's really not. What you do is this. You take in input of a from the previous layer at input, and then you calculate the mean and standard deviation, and then you do this. You zero centering your input, basically minus the mean and divided by the standard deviation, right? And then you get some transform signal. And then what you do is you're gonna scale the signal by some factors here and do a shift, also a learn parameters. But at the result, you have now a output signal, which is a scale and shifted version of the input. And it's only in a scale that manageable by the activation function. So now you learn this, you don't worry about your output signal to go off the board. It's only manageable scale. And you do this for every single layers. So, which I show you here in Keras, if you have multiple layers here, fat layer, some dense layer, you can sandwich that with batch normalization layers in between, right? So for example, this one, after you flatten, you have a dense layer of 300 node, and you have some sort of, initialization here. The batch normalization always makes sure that as signal pass through different layers here, it's in the optimal scale. And at the result, you can see here, you type model.summaries here. There's some few interesting things you can look at. For example, the architecture of the network and the number of parameters. So here, if you notice, the batch normalizations only have 4 times the amount of the number of nodes, because it does learn 4 parameters per node here. So you, for example, you have 784 nodes, you would have batch normalization would have about 3,100 nodes, 4 times at that. And if you have a second here with 300 nodes, then you have about 1,200 parameters, right? Only 4 times the number of parameters in the node. And if you wonder why you have this number, it's simple math. And what you do is this is the dense network, so you had to collect all the input to all the node from previous layer to the current layer. So if you do this math, you said you have 300 node, right? And each of node, this connect to the 784 node before from the previous layer. So that's 335 and 200. And you had to add also the bias term. Yes, we still had to remember the bias term, B. So with that, turned out to be exactly this numbers. So that's how you get to this number, by having just the weight and the bias term. And you do so on and so forth. Each of these will have extra parameters than your regular neural nets. Okay. Now there is a quick and easy way for the batch normalization called gradient clipping, and it's sort of an alternative. It's sort of a quick and dirty way for you to do this. You basically say that you look at the gradient. If it exceeds a certain threshold, then you clip it, so it would never exceed a certain threshold. And this seemed like works some of the time, but not all the time. And typically, they use it more into the recurrent neural net, which will be covered in a few modules. But this is sort of a quick and dirty alternative for batch normalization. Typically, I would recommend you use batch normalization when you do the training anyway. So, and you can do the clipping here directly from the SGD optimizer. All right, so we cover quickly 3 things on optimization of the neural networks. On next video, we're gonna cover the basic optimizer, the optimizer that you adaptive learning rate, and also the second order training method. I'll see you then.